Hello students, in today's class we will read about the effect of dielectric on capacitance. So far we have understood what is a capacitor, what is capacitance, and what are dielectrics. So before I start the topic effect of dielectric on capacitance, just let's recall what's a capacitor, capacitance and dielectric. Seeing the capacitor over here, capacitors are the conductors which are parallelly kept with each other. Conductors parallelly kept. Okay, so these conductors which are parallelly kept have opposite potentials or the opposite charge. If this is having plus q charge, this will have minus q charge. Due to difference in the charges and their polarities, there is a generation of electric field and potential across these two capacitors. These capacitors can be taken as a 3D form of a dipole. Like we have seen a dipole separated by a very small distance of 2a, where one dipole is a plus q and other dipole is a minus q. Polarity of charges do change, but the magnitude of charges remain same in this case. Similarly, here in capacitors also, polarity of this charge is changing, but the magnitude is being the same. There is no change in the magnitude. Now, capacitance, it's the amount of charge that is being held per unit potential is capacitance. So here capacitance can be given by C, that is a constant, and C is equal to Q upon V, charge per unit of the potential. Here, as I said, capacitance is constant because it do not depend upon either the value of Q or the value of V. It basically depends upon the size and geometry of capacitor. Geometry of capacitor. Okay, so this is the basic information of capacitor and capacitance, which will be required while we will read the upcoming section. And now we will move on to dielectrics. So dielectrics are the non-conducting bodies. Non-conducting bodies or non-conducting materials. So we do not say it as insulator, but it is a non-conducting. These non-conductings can be insulators also, but we are not specifying it. So make a note of it. Anywhere the question is asked about dielectric, you have to state dielectric as the non-conducting materials, not as the insulator materials. So dielectrics and conductors have their own differences. Conductors are conducting in nature, dielectrics are not conducting. Dielectrics behave little differently in the presence of electric field. One thing which we need to understand is there are two types of dielectrics. One is polar dielectric, another one is non-polar dielectric. So here polar dielectric, they already have the polarization happened, difference in the positive and negative. There is little stretched about positive and the negative molecules present in the polar, whereas the positive as well as the negative ions center coincide in the case of non-polar. Just see over here, this is a case for polar and this is the case for non-polar. Now what we are doing is that we are providing electric field to this polar and this non-polar. So we'll just see first what happens to a non-polar. The non-polar dielectric will get polarized, as plus and minus ions, and then it will do its function as it should do as a dielectric, which I will explain after a moment. Now when we see this case of polar is already having the two ions or the centers of the two polarity already differentiated. So now we are providing electric field to it. Now exactly what happens in this case is that these polar molecules are randomly distributed in the material. So due to thermal agitation, their overall polarity, the overall dipole moment becomes zero. So when electric field is provided to them, these gets to a proper distribution. They all get oriented in presence of E. These polar molecule gets well oriented. Okay, gets well oriented. Now once they got properly oriented, all the positive charges will reside at one side and all the negative charges in the material will reside on the other side. Due to this, there is a dipole moment creation. So once this dipole moment is created, here also we have polarized and here also dipole moment came, and hence it got polarized. In both the cases, either the polar or the non-polar, what we have received so far is the polarization of the molecules present in the dielectric. This is our main agenda. We have to polarize our dielectric material. Once our dielectric material is polarized, they will be behaving in our providing us the benefit what we need. Now this is a dielectric over here, and this got polarized like this. Here we have a surface charge density which is positive, and at this end we have a surface charge density that is negative. This is capacitor. This is capacitor plate 1. This is capacitor plate 2. Here also they have some induced charges, okay, of different polarity. So here we have one field and here we have another field, okay, field 1 and field 2. See, we have so far generated two different electric fields, one before phase 1 and the other one after phase 2. So that creation of this differentiated electric field basically reduces the overall field. This is F1, F2, which is lesser than the total, the total field is lesser than this. We have introduced a field, initially we have introduced a field F, and now when we introduce dielectric, our field is F dash. This F dash is smaller than F. So as the field intensity is reduced, we will see that other properties have also changed, and how these properties are changing is the thing we are going to read in this topic, in the topic of effect of dielectric on capacitance. So kindly make the note of the above introductory information, now we will move on to our main topic and understand how the presence of dielectric is making the needed or the essential changes in a capacitor's capacitance. So, we will start. We have two large plates, each of area A, separated by a distance d. See, we have two large plates like this, and these plates are like, they have said plate, so I will make it like a plate. Okay, this is the plate. Okay. So these are the two plates, and now we have the like area of this plate is given as A, and the distance separating them is D. Distance separating them is D. The charge on the plate is plus or minus Q. One plate is having plus Q charge and other plate is having minus Q charge, and the charge density is charge density on plate 1 is plus sigma, on plate 2 is minus sigma. So this charge density for any of the plate is given as sigma equals to Q upon A, charge by the area given, because sigma is our charge density for a given area. So we can write surface charge density or area charge density, anything, both are correct. One is, we have already seen, one is linear charge density, other one is surface charge density or the area charge density, third one is sigma, that is rho, that is volume charge density, which is stated generally as the charge density, nothing else. Now when there is vacuum between the plates, what does the vacuum means? Vacuum implies that we haven't introduced any foreigner thing inside the plates, inside the combination of the plates. Still there is no availability of dielectric between the plates. So what will be that? It's either vacuum or the air. Air or vacuum, both are treated equally, because epsilon naught for air is approx to 1, so it doesn't play any significant role. So at any case the value for it will be given as this. Once we are introducing dielectric, this will change to E, which will be epsilon into epsilon of any relative material which is being used. Okay, so this will be changed in this particular formula. Now when there is vacuum between the plates, electric field for the zero existence of any material is given by sigma upon epsilon naught. So electric field is defined as charge density upon permittivity, charge density upon permittivity. Potential difference with respect to the electric field is denoted as V naught equals to E naught into D. In the lecture number 7, we have seen the relation between electric field and potential. We have found out that del V equals to minus of E del L integrated over a given length. So when we are integrating both del V and del L, we will find that V equals to E ds, and here for the V we have taken the modulus. So in any of the cases our magnitude for E doesn't come negative. Magnitude of E don't come to be negative. Okay, this is what we have seen in lecture number 7. Therefore, like we have got equation number 1 from here, equation number 2 from here, equation number 3 from here. Therefore, capacitance C naught in the absence of dielectric material Always remember, node over here is defining node in subscript, is telling us that there is no dielectric present so far. There is no dielectric present so far. Now C node, capacitance without the presence of dielectric is given by Q upon A, charge upon area. So see, here I have made a mistake, it's not area, it's V. As already explained, capacitance is given as charge upon potential. So potential from here we can write. I will do this derivation for you as this is not well explained in the given notes. So I'll just step by step I'll make a explanation of it. Just rubbing it up so that I can create a little space over here to explain it. And whatever calculation I'll be doing right now will be in the absence of the dielectric material. I will write on the above side. In the absence of any dielectric material, capacitance is given as C equals to Q upon V. Then we have V equals to E into D. E can be written as sigma upon epsilon naught. So, and sigma can be written as Q upon A. Substituting the value of sigma from this equation and from this equation substituting the value of E. So, we will find a value for the V. We will do that. E equals to Q upon A, that is the value of sigma divided by epsilon naught. It will give us Q upon A into E naught, and then this value will be substituted in this equation. We will get V equals to Q upon A E naught into D. Okay, we have got the value of potential. Now this value of potential will be substituted over to this equation to find out the capacitance. See over here, I am writing here C equals to Q upon A epsilon naught into D. This Q and Q will get cancelled. So C equals to 1 upon D upon A epsilon naught. So this will go up and we will get C equals to A into epsilon naught by D. See, this is what we are getting, is exactly same as we have written here in the notes. So this is how we have derived and came to the conclusion that C equals to A epsilon naught by D. Now we will start considering something new over here. What is that new thing over here? We are trying to introduce a dielectric between the two plates of introduction of dielectrics between the two plates of capacitance, plates of capacitor. Okay, considering a dielectric inserted between the plates fully occupying the intervening region. Fully occupying implies that thickness of dielectric material is D. Why D? Because we have seen that D is the separation between the plate 1 and plate 2 of capacitor. So, as they say, the intervening space is totally being occupied by the dielectric. We can conclude that dielectric is having a thickness of D. Okay. Hope you got it. Dielectric is polarized by the fields. The effect is equivalent to two charged sheets at the surface of dielectric normal to the field with surface charge density of sigma p and minus sigma p. Sigma p and minus sigma p. How come? See, this is our dielectric. We have capacitor plate 2 over here and capacitor plate 1 over here. This is having a charge of plus q. This is having a charge of minus q. So this end after being polarized होने के बाद, after being polarized, surface 1 will have a charge, and due to that charge we will have the surface charge density to be sigma p. We can define this is sigma p. For this is sigma. P matlab it is the polarization of the dielectric. For that we are defining the surface charge density. Similarly, for this surface it will be plus sigma p, and that is after polarization of our dielectric. This is our dielectric. Now this is also polarized, this is also polarized. So this particular space, see, this particular space will have its own electric field and this particular space will have its own electric field. Okay, so there is the presence of two charged sheet. One is, see, this one is one charge sheet, this one is other charge sheet. If we see it more, we will see like this. There is nothing over here and this is behaving as 1, 2 and this is behaving as 3, 4. We are having this as electric fields are moving like this. Okay, and this space seems to be like a blank space, as in if there is nothing present in this given space. Okay, so after that if we are making a circuit over here, this system behaves as a one unit. From outside this system behaves as one unit, but internally if we see, this system is having three components. One component is the capacitor plate 1 and one surface of dielectric. Another component is the dielectric. Third component is the one surface of dielectric and the capacitor plate number 2. Now the electric field in the dielectric then corresponds to the case when the net surface charge density on the plates is plus or minus sigma minus sigma p. Why we are aiming at the net surface charge density? Because see, our combination is like this. This is dielectric. So this is having one surface charge density, this is having another surface charge density. So overall there will be a charge density which will be the difference between the two densities. These densities will basically add up, but because the densities are having opposite signs, so only we are having a negative sign introduced here. The surface charges will add up. Okay, but one surface is positively positive charge with positive charge density and other surface is with negative surface charge density. Hence, though we are adding, the sign over here shown is a negative sign. So that is, for this we have sigma, for this we have minus sigma p, for this we have plus sigma p, and for this surface we have sigma. So the overall net surface charge density is given as sigma minus sigma p. In the this dielectric polarization, what is one main factor is that the surface charge density on the dielectric will remain lower than the capacitors. At some situations and conditions it can reach up to the equivalent, but will never exceed, okay, will never exceed the surface charge density of the capacitor plate. So now we have seen that electric field is given as charge density upon the permittivity, So charge density, net charge density is given by this, and permittivity is given by epsilon naught. So we will write it over here as such. See, the formula is sigma minus sigma p upon this epsilon naught. Now the potential difference across the plate is given by V equals to electric field into the distance. So electric field's formula can be introduced from this equation. We can write this equation as equation number 5. In the previous page we have seen up to equation number 4. So this is equation number 5, and introducing equation number 5 we have got the equation number 6, which is a relation of potential. Okay, the potential is sigma minus sigma p by epsilon naught into d. For linear dielectrics, now we have seen in our previous chapter 2 that previous topic 2, there is a linear dielectric. So these linear dielectrics show linear behavior. We expect our sigma p to be proportional to E naught. So E naught is proportional to sigma p. In case the initial electric field, this is initial electric field. Okay, so in case E naught is increasing, what will happen to our surface charge density of the dielectric? It will also increase, behave similar as that of E naught. Okay, thus sigma minus sigma p is proportional to sigma. We have seen this thing that, see, I will write here for a better understanding. Make a note of it, I will rub it up. What we have seen is that E naught is proportional to sigma p, and E naught's value in the previous page we have seen to be sigma upon epsilon naught. So this sigma p is proportional to sigma upon epsilon naught. As this is a constant, we can write sigma p is proportional to sigma. Sigma p is proportional to sigma. So from here we can introduce in the equation of potential to get this. Introducing in equation 6. So we get sigma minus sigma p equals to sigma upon k. As this is proportional, this is also proportional. Here k which came in the denominator is also a constant, a proportionality constant. To remove the proportionality, we have introduced this constant k. This constant k is a characteristic of dielectric. It depends upon the dielectric. One dielectric to other dielectric, this k will change. Show changes dielectric to dielectric. If we are taking a dielectric 1, it will have some value of k. But if we are changing that dielectric to some other material, it will have its own different value. So no two dielectrics are same in nature. They have their own characteristic and hence a characteristic constant also. Now see, in case we are having K which is greater than 1, dielectric constant is greater than 1. In that case, potential is introduced as sigma into D upon epsilon naught into K. So, from this equation, we are substituting the value of sigma here. What is sigma? Sigma is charge upon area. So that value we have introduced over here, and we have got the value of potential to be V equals to sigma D upon epsilon naught into K. And from this sigma we have found this as A epsilon naught into K. So our potential is inversely proportional to our constant. V is inversely proportional to our dielectric constant. More the dielectric constant, lesser is the potential needed. Lesser is the potential needed. Now, how is capacitance showing relation with voltage? See, C equals to Q upon V. They are inversely proportional. Inversely proportional. So, C equals to 1 upon V proportional to 1 upon K. So, it will come as C proportional to K. More the dielectric constant of a dielectric, more is the capacitance. More the dielectric constant, more is the capacitance. See over here, the capacitance C with dielectric between the plates is then given as C equals to QV. Q is same as Q and V we are taking from this equation. See on the top corner, C equals to Q upon V. Here V equals to QD upon A epsilon naught into K. Substituting this value of V in this, we will get C equals to Q upon QD upon A epsilon naught into K. This Q and Q will cancel out and hence we will get C equals to epsilon naught A K upon D. So, capacitance, as we have already studied, depends upon the size and geometry of the capacitor plate. Here we see that capacitance is directly proportional to the area of our plate. If the area of the plate is increased, capacitance would love to increase, and the distance between the two plates is given by D. We are seeing that capacitance is inversely proportional to D, inversely proportional to the distance between the capacitor plate 1 and plate 2. If that distance is increased more, our capacitance will start decreasing. But if the distance is lower down, our capacitance will start to increase. For remembering this, let's get one example. You and your friend are there, okay? So you are together for a lesser time. You do not understand 100% each other. Like you need to learn a lot about each other, but your friend gets transferred to some other place. Now you are far away, you are talking less. So in that case, your understanding is not that good. So there is a lagging in the understanding because you two are far away. So your bonding is not increasing. But then one day he get to know that his father got a transfer back to the same place and he comes back. And you start to bond again. What about your friendship? It will flourish. It will grow. So same happens in the capacitance. Separation between the plate is more. Capacitance decreases. Separation is less, capacitance increases. Now see over here, The product epsilon naught into K is called permittivity of the medium and is denoted by epsilon. Okay. So epsilon is written as this. This is our permittivity in media, which is given by permittivity in free space into dielectric constant. Permittivity in free space, epsilon naught is permittivity in free space. And what about K? K is dielectric constant. In case of vacuum, where K is 1, for vacuum dielectric constant is 1. For vacuum dielectric constant is 1. So in that case, epsilon naught equals to epsilon naught into K. So epsilon's value will be, see, epsilon into naught into K, K is 1. So epsilon naught will be equal to the epsilon into naught. Okay. So this will be our equation. So in this case, both are equal. In this case, both are equal. So permittivity for medium is equal to permittivity for free space. Just in case of vacuum or wherever the dielectric constant turns out to be 1. So E naught, epsilon naught is permittivity of the vacuum, permittivity of the vacuum. Now this quantity K, the dielectric constant, is a dimensionless quantity because it is a ratio of epsilon by epsilon naught. Okay. Dielectric constant of substance is a dimensionless quantity. I will write over here because it is a ratio between epsilon and epsilon naught. So K is greater than 1. Whenever K is greater than 1, this K is equal to C upon C naught. K equals to C upon C naught. So see, K is proportional to the new capacitance and K is inversely proportional to the old capacitance. So if K is more, our capacitance will increase. Okay. If K greater than 1, C will be greater than C naught. So what basically happened? It happened so that, like when we are introducing a dielectric between the two capacitor plates, these dielectrics get polarized and get induced charges on their surfaces and a induced surface charge density. Due to this, there is a segregation of the electric fields between capacitor plates, and because of that, the potential required to produce more capacitance reduces. So if the dielectric is stronger dielectric and having a dielectric constant greater than 1, then the capacitance after introducing dielectric increases and will be greater than the capacitance before we have introduced the dielectric into it. Thus, see the conclusion over here. Thus, dielectric constant of a substance is the factor greater than 1 by which the capacitance increases from its vacuum value. When the dielectric is inserted fully between the plates, of the capacitor. Now we have this kind of structures also. When you will solve the problems, you will find that this is a capacitor plate 1 and this is a capacitor plate 2. In this we have introduced a dielectric medium of K1 dielectric constant. Then we have introduced a dielectric medium of K2. So in this case K1 can be equal to K2 or K1 cannot be equal to K2. The thickness of K1 can be equal to thickness of K2 and thickness of K1 cannot be equal to thickness of K2. There will be such cases. A dielectric constant is simply a constant which defines a dielectric's property, but when introduced between the capacitor plate, their thickness also plays importance. Okay, how much area between the capacitor plates is being occupied by a dielectric plays a extremely important role, and this we will understand when we solve few problems related to this concept. Other than that, you will see the problems like these are the capacitance plate 1 and capacitance plate 2, and we are having a dielectric in between. So this dielectric is not one dielectric, but it composed of the 4 different dielectrics of different dielectric constant, 4 different dielectric constant. Okay, so when they are saying that they have got dielectrics of dielectric constant extremely different, then they will say the thickness is same. But if they say that they have different same constant, in that case they can ask you the thickness is different. So in this or the other way they will be asking you question, and we will learn the combination of dielectrics also. Like in the next class we will be reading about combination of capacitor, and soon we will learn a little about the combination of dielectrics too. Okay, so this is how the problems are generated. So when we are defining and deriving this particular concept, in this case when this is our capacitor plate 1 and this is our capacitor plate 2, where is dielectric? Dielectric is present here in the hole. Okay, present here in the hole. There is no vacuum present, it is well occupying. Okay, our dielectric is well occupying. This is what say, fully inserted between the plates of capacitor. Now K equals to C upon C naught. This is our ratio for our dielectric constant, is basically defined for the parallel plate capacitors. See, what we have basically done is that we have defined everything here with respect to the parallel plate capacitors, and we whenever we do derivation and whenever we solve, we assume that our capacitors are parallel plate capacitor to avoid the complications. So this particular formula is for parallel plate capacitor, but this particular equation holds good for any kind of capacitor. Whatever we are reading, we are defining it with respect to parallel plate. One thing always remember, NCERT defines with respect to parallel plate, and even maximum of the time questions are asked with respect to parallel plate capacitors. But we are generalizing and idealizing. We are generalizing and idealizing our concepts. We are generalizing and idealizing our concepts so that they can be used for any sort of capacitors, can be used for any sort of capacitor configuration, any sort of capacitor configuration. So that's all. In today's class we will be reading. Here we have read about the dielectric constant, understood what's capacitor, capacitance and dielectric. Then we have found out the value of capacitance in the absence of a dielectric medium, and then we have introduced a dielectric medium. While introducing dielectric medium, we get to know about two different values. One is the epsilon, that is E, which is the permittivity of a media, and other one is the K, that is the dielectric constant, which is defined for the given dielectric, which is being introduced between the capacitor plate 1 and 2. By the end, we have concluded our study and our derivation by saying that in the presence of a dielectric medium, the capacitance increases, or we can say to produce the same amount of energy or to store the same amount of energy, the voltage needed, the potential from the outside circuit needed is lesser than the original one. So this last statement, I'll give one example and then we will close it up, that if V is the voltage required to produce the C capacitance in absence of a dielectric media, but now we have introduced a dielectric medium. In this case, potential V that is needed is lesser than the initial potential V, and capacitance will be same as C. So the amount of potential needed in the two cases is also different. In absence, it's more than in the presence of dielectric constant. So this actually gives us more scope in the storage. As we have already seen, capacitor is used as a storing energy device, and to store a huge amount of energy, what we need to do is we have to produce a very perfect dielectric and introduce between these two plates. So by using a lesser amount of voltage, we can hold a lot more of energy in the given capacitor. This capacitor plays a extremely important role. See, wherever you want, like the laptop you are using to read, or the mobile phone you are using to read, or any other thing which gets charged and slowly gets discharged. This is all works on the principle of capacitor. Now see, your phone is charged and then slowly when you use, the charge gets reduced up. So this is like before, while charging, our capacitor present in our phone got all the charges from the circuit, and slowly when we are using, these charges are used up. So see, one more thing, the plug you are using, this is having a regulated normal voltage of 220 volts. Like the Indian household gets 220 voltage of the supply, which is an alternating current, AC 220. So see, you are using a mobile phone for that 220, you are using a refrigerator for that 220, you are using a washing machine for it, the oven for it. So these are the home appliances which are big and small, uses less and more energy both. But what basically you are using is the same amount of voltage. So how this voltage is being regulated when we are using a small device and a big device? This is all based on the holding capacity of our capacitor, the size, the shape, the structure, and the dielectric that is being used in between these capacitors. That's how these home appliances on the same voltage are working so properly. Okay, so that's all for today's class. We'll meet up in the next class and we'll read little bit more about the capacitors. So have a good day. Bye bye.